So it gives me great pleasure to introduce Dr. Hidayat Ansari, who is a machine learning scientist too at the Seattle headquarters of Amazon. He has an MS and a PhD in computer science from the University of Wisconsin-Madison, and has a BTech in computer science and engineering from the Indian Institute of Technology, Bombay. Uh, Hidayat's research work as a whole is themed around machine learning, applications to real world data, and in particular, while doing his PhD, his focus was on unsupervised learning, which I think many of you are probably aware of the distinction between supervised versus unsupervised. Over the course of his graduate career, he has worked with both large and wide data sets, spanning data sets of brain scans to proteins to text and other application domains. He enjoys doing exploratory data analysis as well as developing tractable algorithms that are able to process large data sets and get useful information. So Hidayat's expertise spans not only just data science, but as you know, his PhD was in computer science. He is an expert and has taught courses at University of Wisconsin, Madison on data structures and algorithms, C++, compilers, and has expertise in a variety of programming languages, databases, tools, and other computing technologies. With that, I welcome Hidayat. Hidayat was looking forward to speaking with you guys. As always, what you get out of this talk depends on how much effort you put in terms of asking questions. So we should try to make it as interactive as possible. Use the chat room to enter any questions that you have. Hidayat has a wealth of expertise, can sort of, guide you in a number of areas. So here is your opportunity to utilize, his expertise. Okay, with that, Hidayat, over to you.
Thank you, Professor Ansari. So the first lesson of the day is in Murphy's Law, which states that if something can go wrong, it will go wrong. And I'm having a few technical issues this morning, but hopefully we should be able to get through this without my laptop losing power, inshallah. Okay. So are you able to see the slide that says data science careers?
Yes, yeah.
Okay, fantastic, great. Okay, so things seem to be working. Okay, so good evening, everybody. My name is Hidayat, and as Professor Ansari just mentioned, I'm a scientist over at Amazon, and I work on machine learning. And my background is that I went to graduate school in computer sciences, and I focused on artificial intelligence and machine learning. I graduated a while ago. It seems like a lifetime ago now, like 6 years ago. And today I just want to share with you a little bit of what I learned along the way, advice that I did get, advice that I wished I got, and I want to leave a whole lot of time at the end, or even in between, for your questions. And I'm going to keep it pretty short. I don't have a really fancy presentation. Whatever you see on the slides is really just a prompt for me to go off on some tangent and talk about something. So listen, don't just read the slides, and feel free to interrupt me and raise your hand to ask me any questions at any point of time, and we will very likely finish early. Okay, so what to expect in this talk? Like I said, so whenever you see a sort of star kind of thing on the slide, it's a sprinkling of general advice that I wish somebody had given me, or that somebody actually did give me. So I will speak about what data science really is. I'll just give you an overview of the different areas that are involved in it, and I'll sort of walk you through what a data scientist should know and what they actually do in their day-to-day lives. And at the end, I'll mention a few practical thoughts on actually breaking into the field of data science and becoming a practitioner of data science. And finally, like I said, general advice. Now, what is data science? It's a relatively new term. It really didn't exist maybe 10 to 12 years ago. It may have existed, but it wasn't as popular as it is now, the term itself. So data science is not one thing, right? It's really an amalgam, and its meaning changes every day. Is it more statistics? Is it more machine learning? Is it more databases? So it's not a well-defined term, and it really means something different to every different person who is talking about it. And the amount of emphasis you place on each of these fields, on statistics, on machine learning, on optimization, on databases, data management, software engineering, the different levels of emphasis you place on each of these fields leads to different kinds of roles. So you might have, for example, data scientists. You might have machine learning engineers. You might have machine learning scientists. You might have business intelligence engineers, right? So there's a lot of different kinds of roles in the industry, and each of them comes from applying different levels of emphasis to each of these fields. And so data science encompasses, a part of each of these. And beyond this, there's a lot of math involved. So, I spoke about statistics and optimization, and between them, they cover most of the math. But generally speaking, a lot of the math you learned in 11th and 12th grade in high school will come in handy. So calculus, combinatorics, all of these things come in handy in all of data science. And then, speaking from a more pure computer science perspective, you have group theory, graph theory, and all of these, and even data structures and so forth that you will find very useful in data science and machine learning. And the thing with data science is that it's not a field that's set in stone. It's growing every day. There's new math that's being discovered, even today, that becomes part of data science that we didn't think would be in data science. So, for example, I remember I was in graduate school. One of my professors, he said that, I just read this paper on topology, which is a very abstract mathematical field. It's a very pure math kind of field. And he said that, look, I see some overlap between concepts in topology and concepts in machine learning. I don't quite know how to use topology in machine learning, so I'm going to organize a workshop. I'm going to invite some mathematicians, some computer scientists to figure out what we can do. And so he organized that workshop, and there were a couple of really good papers that came out of it, out of applying topology, which nobody had even considered using in machine learning, and applying it for solving a really cool problem in machine learning. So the point is that the field is growing. There's lots of new things happening every day, and it's not something that's set. Okay, and in this talk, I'm going to focus more on what I know, which is sort of the machine learning side of things, and hopefully Uwais has covered another side of it. Okay. Any questions so far? If you have any questions, just unmute yourself and go ahead and speak up, because I can't see the other screen, because like I mentioned, I had technical issues this morning. Okay, I will take that as no questions right now. So why data science? We live in a really unique time. We can use large amounts of data to drive our decision making. As corporations, for example, we can use data to figure out decisions on what products to develop, on what segments of the market to target, right? As medical research facilities, we can use data to figure out where we can optimize doctor-patient time, for example, right? Or treatments. So the reason I said we live in a unique time today is that we have two things. We have both the amount of data and the processing power to make sense of it. And this wasn't true, again, 10 years ago, 15 years ago, 20 years ago. And making sense of large amounts of data is not easy. And this is why data scientists will be in demand, even if most of their job is automated. Okay, so companies, for example, are looking to use comprehensive data to drive business decisions, right? Which part of the market should we enter? When should we launch? Who should we target, right? And outside, the commercial corporate sphere, we want to measure and understand the universe around us, right? We use machine learning, for example, to stitch together photos from astronomical instruments, from telescopes, from cameras in space. We use machine learning to stitch those photos together. We use machine learning, for example, to understand regulatory networks in genes and proteins in our bodies, and everything in between. From the largest of the large to the smallest of the small, we use data to make sense of the universe around us. So the promise of big data, so before we get to the promise of big data, the thing to understand is that computers are pretty stupid, okay? They require immense amounts of data to learn. And I'll talk about what it means for a computer to learn. The promise of big data, and this is important, the promise of big data, at least in the machine learning side of things, is that the more data you have, the better you will perform. Okay, that's one. More data, more performance. And the second premise of big data is that more data is better than less data. Okay, so large amounts of lower quality data are better than small amounts of perfect data. This is another premise of big data that leads to its promise. And there's statistics going around where they talk about how one of the fastest growing job categories, job families, is that of data scientists. So going back to a couple of things that I mentioned about the growth of data science and the promise of data science, the promise of big data. So again, over the past decade or so, a lot of corporations have tried to use big data and data science to drive their corporate decisions. And over the past decade, we've seen a lot of failed promises. We've seen that companies have invested large amounts of money in building data science programs, but they really haven't seen the business output. And that's, there's many reasons, and if I start getting to those, it'll become a little bit more subjective, but largely it's because of a mismatch between promises and expectations. And then another direction that data science is going in is that a lot of it is going to be automated. And so a lot of the work that we do today in terms of data science, in terms of data cleaning, in terms of building models, in terms of building services around those models, a large part of that is going to be automated. But like I said, because this is a field that requires a lot of supervision and a lot of, how do I say it? A lot of interaction supervision from people who know what they're doing, that despite all the automation, despite most of data science being automated, a good data scientist will still have a job. And another reason for the failed promises is that data science hasn't yet adapted very well to the complexity of business decisions. And so it's very difficult to go from abstract theoretical science to core business problems. And so doing that mapping from abstract science to business is, again, a core function of a data scientist. And the better you can do that, the better data scientist you will be. And it's only going to grow. As long as we have data, as long as we have computing power, data science is only going to grow. Some of the things that are challenging to data science, for example, are things that you begin to see a lot today. For example, things like fairness and ethics in AI. And so, on the slide, you'll see something that says predictions is not the same as decisions. So for example, there was a huge controversy, at least in the US last year or a couple of years ago, about how Facebook was using state-of-the-art machine learning in its ads business, right? To figure out, I have this ad and I want to show it to the most relevant people, okay? Because when they show it to the most relevant people, they make the most money, right? And so they want to have each ad be tailored and be shown to just the right set of people so that they can maximize the income that they get from their ads business. And so what was happening was that it ended up being that they were showing ads for desirable rentals, like in the housing market. So, if Facebook has ads to show for rentals in the housing market, they were showing desirable rentals, generally speaking, to white people. And they were showing undesirable rentals, generally speaking, to lower income people of color. And so what that led to was discrimination in who the ads were being shown to. So while machine learning was doing a great job in figuring out who it should target to and maximizing the ad revenue, because it was showing what it thought was most relevant to certain groups of people and maximizing the people that click on it, it led to discrimination in the legal sense. And there's a lot of areas where this happens, right? So especially at Google and other places, especially where you have image recognition algorithms, they do very well on one subset of people and they don't do as well on another subset of people. And so the more that data science begins to get incorporated in government, in corporations, in technology, there's much larger questions now of fairness and ethics. Is it okay to use machine learning, for example, in weapon systems? Is it okay to use machine learning to build social credit scores like in China, right? Is it okay to use machine learning to decide which set of people to choose for a clinical trial versus which set of people to not choose for a clinical trial? Is it okay to use machine learning and data science and artificial intelligence to design self-driving cars? What happens to the people that they hurt? What happens to the cars that they hurt, right? Does the car prioritize the driver of the car, or actually, self-driving cars will not have drivers, but does it prioritize the occupants of the car, or does it prioritize the pedestrians, right? So all of this using machine learning in systems will cause changes in the way that things are done, and they will change, the allocation of harm. Excuse me.
Hidayat, there's a hand
Yes.
up.
Okay,
so
please go ahead. Yes.
Nahir has his hand up, so if he has a question, he can ask it now. Maybe.
Please go ahead. Yes.
Hello.
Yes.
Yes, sir. Assalam.
Sir, yeah, we can hear you.
Sir, my question is, sir, as you said that there are, we can classify data on basically two types, like less quantity data with some less quantity data which has some quality, and more quantity data which has less quality. Okay. So my question is, big data comes into which category? Are both of them comes into big data, or big data is just that data which gives us which leads us to some insights, more insights?
So again, big data is really not a very well-defined term. There's no scientific definition of what big data is. Big data means different things to different people. Okay, so for example, you'll have geneticists come to you and tell you, I have big data, and what they really mean is that they have maybe 50 patients or 50 subjects from a trial, but they have long data sets from them. So from each person, they have their entire genetic sequence, which is a lot of data, right? So you might have the entire genetic sequence, the entire DNA sequence of a person, and you might have their entire clinical history, but you only have this for 50 subjects, which is not a lot of people, right? So this data is very wide, okay? And in other cases, you might have very long data. So you might have a lot of subjects, but you might only have like 5 points of information from each subject, right? So that's very long. In both cases, one could argue that they're both big data. And then you also have cases where you have large amounts of data from a large amount of people, right? So big data is not really a very well-defined term. Now, there are definitions in terms of volume and velocity and so forth. So I don't like to talk about what big data is because it just means different things to different people, okay? Generally speaking, however, when it comes to machine learning, you want to err on having more data of slightly lesser quality if required, rather than small amounts of data with very, very high quality, generally speaking. And this is in order to boost your prediction performance, for example. So it's best not to get hung up on what is and what is not big data. It just depends on what your application is, okay? So if you're the geneticist and you have large amounts of data from 50 people, from a machine learning and statistics perspective, you can't do a whole lot with that. Even though you have tons of data, you can't do much with it, okay? So And yeah, does that answer your question?
Yes,
Or
sir. Yes,
that's
sir.
gonna
Of course. Yes, sir. Yes, sir.
give
You
you
did. You
a
did.
new
You
way
did.
of okay,
You did,
fantastic.
sir. Sir, one more question.
Sure.
Can I ask, sir? As you said, that data science term didn't hasn't come into play 10 or 15 years ago. So my question is, sir, that data is being generating from since a long time. It's being generating since a long time. So
Yeah.
what's I mean, my question is, what has made the term data science come into picture?
So, like I said, so there's two things, right? You need two things for data science to become as big as it is today. One is the availability of data, and the second one, the more critical one, well, maybe not the more critical one, but another critical one is the computing power. So 10 years ago, 15 years ago, you didn't have the computing power to sort through this data, to run analytics on it, to run machine learning on it, to build models off of it. You just didn't have the computing power. And so what happened 10, 15 years ago is that we started having distributed computing. We had great advances in distributed computing. We had great advances in distributed algorithms, right? Things like Hadoop, things like Spark, right? Where you have large amounts of data, and now you're able algorithmically and infrastructurally to split that data up, to farm it out different computers, to perform computations on that data, to have them send it back to you, and to make sense of it. So that's what happened in the late 2000s and early part of this decade, or early part of last decade.
Yes, sir. Yes,
Does that answer your question?
Okay.
Okay.
Yes, sir. Yes, sir.
And the thing is that we have been collecting data for a long time, but we're collecting much more data now, right? So for example, if you just think about the number of images that are being uploaded to Facebook every day, right? It's in the hundreds of petabytes. Every day, hundreds of petabytes of images are uploaded to Facebook today. But 10 years ago, that wasn't the case. And 20 years ago, there was no Facebook, right? So
yes,
while there was data available, it just wasn't being captured and stored. And now we have the ability to measure a lot of different things, and we have the ability to store it very cheaply, right? So that's the difference.
And I guess smartphones are played a big role in promoting data science.
Absolutely, yeah. So smartphones, sensors, and all the other things that capture and store data. Anybody else have any questions?
There is a question in the chat.
Okay.
I think which you probably will cover. So the question is that, this is a question from Vineet, that he has finished Python basic, and he's wondering whether machine learning is a good path for him. So I guess the broader question here is, what does it really require to be able to get into this field? Is it something that everybody should focus on or not? We are talking of BTech and undergraduate students here, and so what is the right time, what is the right path, etc.
Sure.
Which you will probably cover either later or now, whenever you want.
All right, I will cover this later. So Vineet, if I don't answer your question later, please ask me again, and I will cover it in more detail. Okay, so let's continue. So like I was saying, so fairness and ethics is really going to grow. So for example, is it proper? So Facebook has viral algorithms, right? So it has algorithms that pick out certain stories and post on Facebook, and when it sees that it's getting a lot of engagement, it makes it more popular. So it gets a virtuous cycle going. So somebody posts something on Facebook, 10 people like it instantly. Facebook says, well, this is popular. Let's show it to more people. And then 100 people like it. And then Facebook says, well, this is really, really popular. It must be something very good. And then it popularizes even more. And then it gets thousands of views and tens of thousands of views. So this is all run by AI. So the fairness and ethics question is, should it matter what's in the post? Should it matter whether it's fake news or not? Should it matter whether it's incitement or not? Right? So this is a fairness and ethics question. So data science is getting very good at what it does, but at the same time, there's big challenges in terms of fairness and ethics, and the research in this area is only going to grow. Okay. So, also, I just learned recently that one of my former colleagues is using AI for agriculture. So they use drones to take pictures of large fields. So, in America, you have very large fields and very few people, right, in the farming industry. And so it's difficult for a few people to handle, hundreds of acres of land. So what they do is they use drones to understand what's happening in the different areas of their farms. And so they use AI to figure out whether crops are growing to the level that they should be growing, whether they're not, to measure the amount of pests and so forth. So, AI is used in all sorts of areas today that you'd be very surprised to hear about. Okay. So I want to talk a little bit about the different fields that I mentioned at the beginning of this talk, just statistics, machine learning, and optimization, and so forth. So again, as undergrads, as soon to be graduate students, perhaps, it's really good as a data scientist to have a basic understanding of statistics. At least take Stats 101 or Stats 102, right? And you want to understand about the different kinds of statistical distributions out there, the different kinds of statistics on those distributions, to understand how to estimate certain things. So for example, if I tell you that, there's a population of 1,000 people and I want you to estimate what is the average height, right? It's possible to do that with 1,000 people. But if I tell you that there's, 1.4 billion people in India, and I want you to estimate the average height of a person in India, you can't go around measuring the height of 1.4 billion people, right? So how do you estimate the height of 1.4 billion people? So again, you have to use statistics. So you use sampling, and then you use data from that sample to estimate, what could the height be, and then you estimate the bias in your estimate, and so on and so forth. So there's a lot of different concepts and statistics that will be useful to you as a data scientist. You just want to make sense of some data. So you've all heard, for example, of A/B testing, right? Where you have a new feature and you want to test it on some customers and not test it on some other customers, right? That's a very simple application of an A/B test. So suppose you run your A/B test. How do you make sense of the results? How do you know if A is better or if B is better, right? You have to know statistics to understand how to understand the results of your experiment. When you go back to your business stakeholder, what do you tell them? Do you tell them that, well, I know for sure that A is better? And then the question is, how sure are you? How do you answer that question? How sure are you that A is better? And second question is, how much better is A than B, right? If it led to, for example, 10,005 rupees in sales versus 10,000, that's not much of a difference. That could just be a statistical glitch, right? So you have to answer all these questions, and statistics give you the language to answer these questions. How sure are you, and how much more is something than the other? Okay, so it's very useful to have a background in statistics to be a functional and to be an effective data scientist. Okay, so machine learning and optimization. Machine learning is where you use past data to make predictions on future data, right? Just very generally speaking. So you make predictions on unseen data using patterns that you found in past data, right? So you might, for example, train a machine learning model to recognize the difference between mountains and, say, lakes, okay? And then you give your model a new picture that it's never seen before, and you ask it to predict whether it's a mountain or a lake. Or, for example, you train it, for example, to understand the difference between a cancerous scan and a non-cancerous scan, and then you have a brand new patient come in with their scan, and you ask your model, is the scan cancerous or non-cancerous? Okay, so machine learning is where you make predictions on unseen data using things that you learned from seeing in past data. And then that's supervised machine learning. And with unsupervised machine learning, it's more of an exploratory tool to understand what are the patterns in your data. So you don't have labels on them. You don't have labels that say, this is a picture of a lake, or this is a picture of a non-cancerous prostate, for example, right? So you don't have these labels, and you just want to sort of explore your data. You want to see how your data is clustered together, okay? And then there's supervised machine learning, which is where you have some labels on data and you want to make predictions, okay? And then one of the really popular fields today is called deep learning, which is really just supervised learning, but it uses neural networks to do the supervised learning. Now, it's a very, very active area of research right now. And again, to be very simplistic about it, we still don't know how it works. We know how it works. We don't know why it works, right? These models, the deep learning models, is very deep, very wide neural networks. sometimes they have billions of parameters. And given what we know from classical machine learning, we really don't know why these things work. They work very well. Deep learning works very, very well. It's revolutionized machine learning, okay? 10 years ago, there was no, okay, let me qualify that. I won't say there was no deep learning, but it was not a very active research field. In 2012, you know, so if you look up, you know, ImageNet, and if you look up, you know, the Google Image Challenge, in 2012, you know, they made a breakthrough, right? They found the right loss functions, they found the right network structure, they found the right computing power, they found the right data. And so it's really taken off since then. And so it's an area of active research. There's a lot of research in making it better, a lot of research in understanding why it works, like I said, and then a lot of research in actually using it for other areas. So deep learning is something you really want to sort of get a hold of if you want to get into machine learning. And then how does machine learning even work? So underneath the hood, underneath all the fancy talk about predictions and past data and learning and all of that, underneath all of that is simple math. It's just math, right? It's calculus, it's discrete optimization. And so, you know, all of the things you learn in high school about finding the maximum of a function, finding the minimum of a function, multivariable, calculus, that's what's under the hood, right? So you have to know these things really, really well. You have to understand exactly how gradient descent works, you know, where it might fail, what does failure mean, and you know, a bunch of other discrete optimization algorithms. Okay. Now, okay, so the others, okay, so how is machine learning different from statistics? You might think that they're the same. So again, from a very, very high level, very simplistic perspective, statistics allows you to make assertions about large populations, okay? So statistics might say, here's how you estimate something about a population. Here's how you infer this parameter about this population. Here's a confidence interval for this parameter. And machine learning, on the other hand, it makes predictions. It makes predictions about individuals, okay? So statistics is generally about inferring parameters from populations, and machine learning is more about making individual predictions on individual data points. Now, they each use each other. Machine learning uses a heavy dose of statistics, and statistics is beginning to use a lot of machine learning tools now, but that's how they're different, okay? So statistics is a language that machine learning uses to make its assertions, okay? So for example, what I said way early in the talk, how do we know that more data improves performance? How can we prove this, right? It's one thing to just show it and say that, well, on this one application, if I have, you know, 10,000 training examples, I get, you know, 90% accuracy. And if I have 100,000 training examples, I get 99% accuracy. It's one thing to say that it works on one data set, but how do you say in general that more data will lead to better performance? So statistics give you the tools to prove these kinds of assertions. Okay. Now, another area of data science is data management, where you're really more concerned with just managing large amounts of data. So how do you store it? How do you locate it? When you have terabytes and petabytes of data, how do you find, you know, one specific piece of information? How do you do it efficiently? How do you not take hours to do it? How do you do it in a few seconds? How do you manipulate large amounts of data? You know, you have data in one warehouse, you have data in another database, and you want to join on a specific field. How do you do that? So again, go back to your database classes, right? So presumably all of you have had database classes. So how do you do that with petabytes and petabytes of data? How do you validate data? How do you make sure that it's sane? How do you make sure that you know, the data actually makes sense, that it's not nonsensical, that, you know, the amount in someone's bank balance is not negative, for example, right? That's very simplistic, but how do you make sure that, you know, one row of data actually makes sense with everything else in it, right? How do you know that this person doesn't have two different locations at the same time, okay? And then, you know, there's a term on the slide, which is called ETL, extract, transform, and load. So this is a way, again, of manipulating large amounts of data, of extracting information that you need, of transforming it, and then of putting it back in the database. So these are all, for example, each of these is a separate job, right? There's data scientists whose entire job it is to store, manipulate, and validate data. There's entire data scientists whose entire job it is to do ETL jobs, okay? And then as a data scientist, you want to be familiar with data manipulation algorithms like MapReduce. MapReduce is actually not being used at all today, or not very much today, in favor of more advanced technologies. But MapReduce is very good to know conceptually, right? To understand what it does. How did MapReduce transform the way that we deal with large amounts of data, right? To understand that paradigm. And then how did Spark come along and turn that on its head and say that, well, I'll do everything in memory, okay? So there's a lot of technologies in data management that help you to deal with large amounts of data. And usually when people say the term big data, they're really talking about data management, about storing, about locating, about manipulating. They're talking more about that side of things rather than actually running machine learning on them. So when most people say big data, they're talking about data management, okay? And there's software engineering as well. That's a core part of data science. Oh, I thought I had more on here. Sorry. I think I modified the slides after moving it here. But so the software engineering side of things, you have to know how to build models. You have to know how to make services around those models. So it's one thing to build a model on your laptop or on a computer, but then how do you make it available for it to handle 10,000 queries every second, right? You know, when you work at a large firm like Amazon or Microsoft or Google or wherever else, you have to build these services. You have to build these models that can handle things like 10,000, 50,000, 100,000 queries per second, right? So how do you build the infrastructure around that? So that's the software engineering part of things. And this is also part of the role of a data scientist, to not only build the models, but to build the infrastructure around it, right? How do you build a distributed computing that allows for a model to serve that much and not go down, right? And then you also need to build visualization tools. So how do you understand the results of a machine learning experiment? How do you understand the results of a machine learning model in production, right? How do you visualize? And I'll go through some examples. Actually, towards the end of my talk today, I'll go through some examples, some really nice examples of how people visualize data and results and insights from data. So the roles in data science, they run the gamut, right? Between purely engineering or more engineering-oriented roles. So for example, building a service around machine learning model that's more engineering-based, and then more data management type of roles, where most of your day job is you work on ETL, and then more research-oriented roles where most of your job is really just focused on analyzing data, on building models around it. And it's rather rare for one role to do all of it, from research, from business to research to data management to engineering. So mostly, you'll find roles that are on one end of the spectrum or the other or in the middle somewhere, but rarely will you find a job or a role that covers every single thing. So it really runs the gamut. So you might hear the term data scientist, you might hear the term machine learning engineer, you might hear the term research scientist or applied scientist, you might hear the term business intelligence engineer, a data analyst, a data architect. So all of these have different meanings, right? Some of them might focus more on data management side of things. Some of them might focus more on how do we analyze large amounts of data and present them to business stakeholders, right? That's a job by itself. Okay, so let me pause here and ask if there are any questions, and then I'll get into more the how thing. So now that I've talked about what data science is, and what's sort of involved in the different kinds of roles, we'll pause here for questions. Does anybody have any questions?
Sir, hello?
Yeah,
May I,
go ahead.
May I, sir? Sir,
And one second, Shahir, just let us have a few other questions before we
okay.
come to, Wes, do you want to handle the questions?
Yes, I can handle the questions.
Okay, so go ahead. Hidayat, Wes Siddiqui is also
fantastic.
on the call. Yes, and there are many other mentors. So just
awesome.
alert you. I think Wes is better suited for this task than I am. So
Definitely.
the two
The first-
Amazonians in data science.
Thank you so much. So Hidayat bhai, the first question is basically, can you elaborate in detail a journey from like an entry level position for a data scientist and then eventually like working on more complex data science projects? This is a question from Malik.
Okay, so I'll get to that a little bit later, but briefly, the journey, I mean, so this is a question of professional development, right? So it's not specific to data science, but essentially, you have an entry-level position. It's about professional development. It's about positioning yourself to excel at the work that you already have, and positioning yourself to receive work and projects that allow you to demonstrate your skills and capabilities, right? So be very good at what you do and propose new ideas or assign yourself more work that allows you to shine at the next level, right? So it's about finding those opportunities, creating those opportunities. If you see a business problem, construct a solution for it, and grow yourself. So it's really more about professional development. It's not specific to machine learning or data science, right? This is how you would grow in any role, as a program manager or as an engineer. Does that kind of make sense? Always, you want to add anything to this?
No, I think that makes total sense.
Yeah, I mean, it's a little abstract, but I mean, that's what I'm saying, right? So you're an entry-level person now. You're very good at what you do. You deliver on time. You deliver insights on time as a data scientist, and then you identify other problems, and you say that I have the skills to solve the other problems as well. And so you grow your skill set, you grow your visibility, and it's about earning trust of people, right? So people trust you to look at data, to come up with actionable insights. And so the more you do that, the more trust you earn, and the more you distinguish yourself as an experienced and senior data scientist.
Just to
Exactly.
chime in, Malik asked this question. So Malik, if you want to unmute yourself and ask whether, what you actually wanted to ask in terms of, your question, and whether this answers.
No, I think I think my question was answered.
Okay, very good.
Yeah.
Thank you.
Robert. Thank you so much.
Awesome.
Great. Like Hidayat bhai mentioned, basically starting with smaller problems and then progressing into more complex ones. And an essential part of that is identifying the problems. And as you work with partners within whatever business that you're a data scientist for, you start identifying those problems and we'll start building out solutions. So moving on to the next question. I'm not sure if this was answered. What is your opinion of the future of data science in healthcare, considering the present COVID situation globally?
Well, I mean, that's two separate questions, but data science in healthcare is only going to grow. The only constraint that data science has in healthcare is patient privacy, right? So as a data scientist, I want tons of data. I want to gather information from all the hospitals across the country. So if I'm researching prostate cancer, for example, and I want to build a model that is able to figure out, what's the best course of treatment for prostate cancer, right? If I go to one hospital, I might find a few dozen subjects, a few dozen patients. But if I gather data from all the hospitals across the country, I'll have thousands. And as a data scientist, I want thousands. I don't want dozens, right? But then there's patient privacy concerns. So not all the hospitals want to share their data because there's concerns about the privacy of healthcare data. So there's a lot of research around anonymization, around privacy preserving analysis and stuff like that. So and healthcare is one area where, again, AI has not reached its full potential. And so as far as the future goes, there's a tremendous scope for applying healthcare and machine learning. I mean, think about the Holy Grail, right? You go to a doctor. Maybe you don't even go to a doctor. Maybe you have a machine at home that okay. I need to resituate myself. I'll be right back. I apologize.
I'll pick it up from here. I'll answer one
Please
question
do.
at a time
Okay.
while you
Okay.
sort of figure that out.
Yes.
So there's one other question from a student which says, like, is being a
So,
data scientist?
Owais, if I may add a little bit to what Hidayat just said, one of the challenges of finding the right applications in healthcare is that machine learning is not an exact 100% accurate science. So any domain that can tolerate a certain level of inaccuracy, say 98, 99% accuracy, is very well suited. But if you need 100% accuracy, we are not there yet. So that is one other hurdle in terms of applying machine learning and data science for healthcare applications.
Absolutely, Najib Saab. I think that answers it, puts it well. Hopefully that answers the question for Allah Baksh Saab. Moving on to the next question. Is like being a data scientist very hard? I mean, does the job have more pressure as compared to CS fields? I would say not in particular. It depends on how well equipped and trained you are and what your skill set level is. These are two separate fields, computer science and data science, and they've got their own underlying skill set that you need. Somebody who's from a CS background needs to be able to code well, program well, problem solve as well. Somebody who's a data scientist also needs to be able to do that, but there's some additional theoretical knowledge that they need to work on, being able to recognize the right algorithm to work with. How do you go ahead and build out a model? The coding may not be as intense in terms of building out end-to-end solutions, but there is a coding component involved where you are building out a model. So I wouldn't say like for this student in particular to think of it from that perspective or make a decision based on how difficult it is. Take a decision based on how interesting do you find that specific area. Great. Does any of the additional mentors want to add anything there? Or and looks like Hidayat Bhai is back.
Yes. Okay. Can you see my screen now?
Great. So yeah, I'll just share the next question and Hidayat Bhai will continue.
Okay.
So the next question is basically, should we focus on one aspect of data science? For example, focusing on data engineering in particular, or should we focus on a broader scope, which is like machine learning, statistics? So how do you sort of work on specific, but I think the question is pertaining depth versus breadth, even particularly within machine learning.
Great question. Again, so I'll cover this maybe a little bit more later, but briefly, there's plenty of room for all kinds of people. So you should focus more on what you're good at, what you have the aptitude for, rather than what you think is most in demand. Everything is in demand, right? We need competent software engineers. We need competent data management people. We need competent scientists, and we need competent people of everything in between. So if you have an aptitude for a certain area, you will do much better there than you will in choosing something that you think is more popular today. Does that make sense?
To the questioner, does that answer your question? I think the questioner was Shakil. If you could unmute yourself and answer.
Yes, it's clear.
Okay, awesome. So maybe I'll speak a little bit more about these roles. Oh, sorry, are there more questions, Wes?
There are a couple of more questions, but what you could do is continue with the presentation and then we could pick it up at another break.
Okay, let's do that. Yeah,
Great.
I don't think I have a whole lot left. So, and probably getting to the actual, hitting the ground stuff. So maybe we'll have more questions then. Anyway, so let me speak a little bit more about these roles then, because it seems like we have some interest in what these roles actually are. So a data scientist might, for example, invent new approaches or algorithms to analyze data, right? So you have a large data set and you want to understand, what can this data set tell me? What are the interesting action items that I can take from this? Is there an interesting way of segmenting this market? Do we have clearly, say, 5 different types of customers, right? So that's what a data scientist might do. A data engineer, for example, I don't have that on my list here, but a data engineer, for example, they might build the underlying infrastructure required to use that data at scale on a continual basis. So if you have petabytes of data, you might have a data engineer build pipelines and optimize how we store that data and make it easy to fetch what you're looking for. So that's what a data engineer might do, right? A data analyst, for example, they might apply algorithms to help business leaders interpret data. They might think about what decisions should be made from data analysis versus what should be informed by heuristics, right? So there's actually a saying at Amazon, and I believe it's attributed to Jeff Bezos, where he said that if the data tells you something and the customer anecdotes tell you something else, you should believe the customer anecdotes, right? Which kind of goes against what I've been saying for my whole talk, but it really doesn't. What it tells you is that your data analysis is incomplete and it's missing something, right? So you might have a data analyst that looks at both of these things, that looks at both anecdotes, heuristics, and also looks at raw insights from data. And then you might have a data architect, you might have a business intelligence engineer, and what they might do, for example, is make dashboards to collapse and summarize information from large amounts of data so that people can consume it, okay? So how do you become a data scientist? This is one of those fields where it's pretty democratic, right? It's not about where you come from. It's not about, you know, did you go to the best school or not? You know, it's less about who you are and more about what you know, okay? So if you know the right things, you're in, right? Your path to becoming a data scientist is very smooth. So I work with colleagues, for example. I'm sorry, is there a question?
No, I think there was some unmuting by somebody.
I see, okay, okay. So I was saying that I work with people who have PhDs in physics. Can you please unmute yourself, please?
I went ahead and muted that individual.
Thank you so much.
I'll manage that.
Thank you, always appreciate that. So, like I said, I work with people who have PhDs in theoretical physics, for example, people who have PhDs in electrical engineering, people who have backgrounds in pure marketing, for example. And so, if you know the right things, it's very easy to become an effective data scientist. And again, it depends on what kind of roles interest you, right? So there's many different routes or paths to becoming a data scientist. Now, my particular path was more research oriented, right? And in my case, I would have preferred to stay in academia and teach and research, but it didn't work out. So my path was graduate school. I learned how to research, solve problems, how to do original research, how to publish, and then go back and repeat. There's other equally valid paths that are more hands-on, where maybe you might begin as a software engineer, maybe you get your hands a little bit dirty with data analysis, maybe you find that you like it a lot, maybe you learn a little bit more about the algorithms involved, maybe you learn a little bit more about the math involved in analyzing data. And so there's many different routes to becoming a data scientist. So focus on the skills that you need or that you want or that you have some kind of aptitude in, right? Get down and dirty with data. Find interesting problems to solve. I'll go over some examples at the end of this talk, okay? There's so many data sets online. In 2021, there's so much data online that, compared to, again, when I was starting off in graduate school a long time ago, it's just a very different landscape, right? Back then, you had to scrounge for data. And now there's just so much data available online and it's openly available. It's not hidden behind paywalls or hidden behind universities and corporations. So what I want to say here is that, again, going back to something that I said earlier, right? Value yourself. You want to value what your aptitude is, what your skills are. Don't rush after what is currently hot. Don't rush after what you think the industry currently needs. In the general field of data science, we need everybody. We need all kinds of skill sets. Okay, so value yourself, grow yourself, think about yourself as something that you nurture. Think about your skill set, and treat yourself and be good to yourself, because you're growing your skill set, you're growing your own brand, you're growing who you are and what you can contribute, and how you can make sense of data. Okay. Now, what do you need to know, right? What are the essential things you need to know? You need to have a really good background in math and programming. Like, this is the basic, right? When you think of data science, you don't automatically think of math and programming, but you have to know math and you have to know programming. You have to because if you don't know math, then you'll be applying machine learning algorithms, you'll be applying data analysis algorithms, you'll be applying summarization algorithms to data. And if something goes wrong, you won't even know it's gone wrong, because you don't know, for example, that this kind of data is not suited for this kind of analysis, right? You might not know that if you don't understand, exactly what, gradient boosting is, for example, and you apply it to a data set where, you really can't trust all the labels, right? So that's a big mistake. And so you have to know the math behind algorithms to be able to do effective data analysis. And then you have to program, right? When you work with data, you have to program computers to manipulate large amounts of data. And so you have to have a solid background in this. And all of you are undergraduate students, and so you should have had exposure to math and programming by now. And if you haven't, then I would advise you to use the remaining time in your undergrad to really shore up and to really build the skills in discrete mathematics and in coding effectively. Okay. And again, concepts are much more important than buzzwords. So a buzzword is Hadoop. A buzzword is TensorFlow. A buzzword is I don't even know all the buzzwords that are in use today. But to understand what Hadoop does, to understand mapping and reducing, to understand data distribution in Spark, to understand what goes on under the hood, that the concept of that is much more valuable for you to know than to be able to put a word on your resume. Okay? To invest in yourself, to understand, is much more valuable to you in the long term than to maybe spend one day learning about how to talk about Hadoop or something. Okay? So focus on concepts, don't focus on buzzwords. It's okay to have fewer buzzwords on your resume and have more concepts. Okay? What does the data scientist do day to day? Again, there's different types of data scientists, but generally speaking, there is one sort of ugly truth that is generally not spoken of, which is that a large part of your time will go in cleaning up data. Okay? The data in the real world is not neat and tidy and perfectly labeled. There's missing data, there's corrupted data, there's inconsistent data, and so a large part of your day will go to locating and cleaning data. Okay, it doesn't matter what part of the spectrum you're on, whether you're a BIE, whether you're an applied scientist, it really doesn't matter. A large part of your day will go in cleaning data. And otherwise, another thing that a data scientist does is that they translate business into science, right? So you have a business problem at a corporation, and it takes a specific kind of skill to translate that business problem into a science problem, and coding it, finding the right kind of data, prototyping a solution, and then productionizing that solution into something that business can use. Okay. So maybe let's go back to a little bit about essential things to know. So I just thought a few more examples, so we can go back here. So the thing that you want to know, for example, so there's algorithms in machine learning, like, there's clustering algorithms like k-means, for example. You might have heard of this. There's algorithms like support vector machines. There's logistic regression. There's, even basic linear regression. So what I want you to do when I talk about concepts over buzzwords, what I want you to understand is what is the data flow happening here? how does the algorithm work? What happens when you can't fit the data into the memory on one computer? How do you distribute it? How do you break down the problem? And how do you distribute that breakdown to different computers and get them to compute things? And how do you make sense of the results together? How do you distribute it? How do you iterate over it, right? How do you parallelize? So if you understand the math behind an algorithm, you'll be able to answer all these questions I just asked, okay? So what you want to do is you want to position yourself for success after the buzzword dies out. Hadoop was big for maybe 7, 8, 9 years, and then it died out, right? And so you want to position yourself for success after that fad goes out, right? It's about the concept, it's not about the tools, okay? Okay, so let's get back to the day-to-day with data scientists. So again, the untold ugly truth is that it's all about the data. It's all about finding it, making sure it's valid, making sense of it, making sure that the model of the problem is right. So you might have a business problem, and then you might translate that to a science model, making sure that the transformation is correct, finding the outliers, and figuring out what to do with missing data. This is the untold ugly truth of the day-to-day of a data scientist. Okay. Another day-to-day of a data scientist, maybe a certain kind of data scientist. Just for fun, I went to my Stack Overflow page, and back in the day, I one of the ways that I blew off steam was that I used to answer Stack Overflow problems. And so one of the things that I really liked doing was to find problems where people were complaining about how, this piece of code takes 2 hours to run on a machine. I need it to run in a few seconds. And so I used to love finding those problems and finding ways of speeding up computations, right? So when you deal with millions and billions of rows of data, you want to have fast ways of dealing with that. So here's an example of just taking a large number of numbers and just calling the log function. Just calling the log function on a large number of random numbers. So here, this is R. This is language R. And in the first line of code, we're just sampling 1 million random numbers, okay? And now the first half of this code sample, we're running a loop, okay? And we're calling the log function individually on every element in the loop, okay? And this takes, a very long time. Now, if you use something called vectorization, which is that you use inbuilt system optimizations to run some things in parallel, or not so much in parallel, but to use internal system libraries to compute the log. If you look at the speed up in the time, for 1 million numbers, in one case, it took 1.9 seconds, so about 2 seconds, okay? And in the second case, when you use something called vectorization, it took 0.017 seconds. So it's about 100 times speed up. Now, what if you had not 1 million random numbers, but what if you had 1 billion random numbers, right? It would take you 2,000 seconds, if I'm doing the math correctly. It would take you about 2,000 seconds versus just taking about 20 seconds, right? So there's a big difference, a half hour versus 20 seconds. And this is a very contrived example, right? There's other things you can do. So somebody else asked a question about, I have an image, I have an RGB image, and I want to figure out how many white pixels there are in the whole image, okay? So you can do it by going through every single pixel, going through every red, green, and blue value, and checking if it's 255. Or you can do it in a vectorized way and do it much faster. So, here's a line of MATLAB code, for example, that does it in one line and does it very, very fast. There's another example where somebody wanted to figure out, I forget exactly what I want to figure out now, but I was able to reduce, the code on the left with 2 lines of code and running much faster. So a large part of your day as a data scientist will also go in optimizing code and making sure that you can run code faster and achieve the same results. So again, you have, knowing programming, knowing data structures, and knowing how they work will really help you in your day-to-day as a data scientist. I'll go over a few books that you'll find helpful to you as you grow as a data scientist. This is a book that I have on my shelf, and I consult it, at least once a week. It's called All of Statistics, and it's by Wasserman. It doesn't contain all of statistics, obviously, but it contains, most of what you need to know. So it's a really good book to go through. There's another book called The Elements of Statistical Learning by Chip Shirani out of Stanford. And again, it's a good book that it's sort of a good reference to understand, classical machine learning algorithms. How does logistic regression work? How do support vector machines work? How does regularization work? Why does it work? Right. So it's got all the theoretical concepts, and it's got a really good explanation of classical machine learning, not so much deep learning, but the other fields. And there's another one called Pattern Recognition, PRML, Pattern Recognition Machine Learning by Christopher Bishop. Another really good book to have. And a more recent book by Yoshua Bengio and Ian Goodfellow called Deep Learning. Again, so this is more specific to deep learning, right? So how does it work? Why does it work? What's backpropagation? How do you propagate gradients? What are the different problems you can run into? And there's a more recent book by Kevin Murphy called Machine Learning, A Probabilistic Perspective. So these are sort of some of the books that I would highly recommend you to at least peruse and go through to understand, where your aptitude is, what you want to learn more of. If you're into reinforcement learning, if that's something you want to explore, and again, this is something that's growing a lot, especially deep reinforcement learning. There's a book by Sutton and Bardo, which is considered sort of the textbook for reinforcement learning. And as again, more towards the science side of things, you want to keep up with conferences and journals. So you want to keep up with, for example, the International Conference on Machine Learning. You want to keep up with Neural Information Processing Systems, the Association for the Advancement of AI, Computational Linguistics, Computer Vision conferences. All of these conferences, they publish their proceedings online. So you can go through, the past 10 years, and you can see, what are the best papers of every year in each of these conferences? What problems are they solving? Why are they problems? What is so clever about the way that they're solving these problems, right? So this will give you a sense of where the field is and what the problems are, okay? And this is, again, sort of more in a researchy way, okay? The software that you need to know as an engineer, right? Today, a lot of data science is done in Python, so you want to be very proficient in Python. You want to understand, sort of some of the deeper ways that Python works, the programming language aspects of Python. R is also used, not as much now. R was more popular a while ago, R and MATLAB. But R is, again, good to know. There's some things that you can do in R. So, for example, linear regression and building multivariate models and so forth. It's just much easier to do in R than it is Python. Python has a way to catch up in that area. You want to be very familiar with SQL and other data querying languages. And within Python, you want to be familiar with the scientific computation packages called NumPy and SciPy and scikit-learn and pandas and so forth. You want to be very familiar with these. And if you're doing deep learning, you want to know Keras or TensorFlow. So Keras is a package that's built on top of, it sort of abstracts out some of the more low-level functionality of TensorFlow. So you want to know Keras, or you might want to use PyTorch, which is out of Facebook, which is slightly more. They both have their pros and cons. But if you want to do deep learning, then you want to be familiar with PyTorch or Keras at the very least. Okay, and again, I cannot emphasize enough how important it is that you are very good at core computer science, right? Core systems. So I remember a time in graduate school when we were building something for text prediction, and we needed to look up word co-occurrences in a very, very large corpus. I think it was a few terabytes of data. And we were doing that in MATLAB at the time, and each query for each pair of words was taking us about a couple of seconds. And we had done as much optimization as we could. And we needed to look up millions of these. So we're talking about millions of seconds here, which is just unworkable, right? We can't wait millions of seconds to look up something in data. And so one of my colleagues, he was actually a systems researcher. And what he did was he understood exactly how file I/O worked in Linux. And so he built us a system that was very close to the OS, and he built us a way that we could look up these word co-occurrences very, very quickly. So we could look them up in a fraction of a second. I think it was like, a few milliseconds each. And so when we had to do millions of these operations, it allowed us to finish the analysis in a couple of days rather than wait months. And so the more core computer science you know, the more systems, the more programming language, your PL course, the more beneficial it'll be to you as a data scientist. Yeah, okay. So how do you come up with a project idea? So again, I would highly recommend going through these journals and conferences, because it'll give you an idea of where the field is currently, what the future directions are, and it'll build you an important skill, which is to go through a scientific paper and to understand, what problems they're solving and what they're applying, what math they're bringing to a problem, and what assertions they're making, and so forth. So how do you come up with a project idea? Think of a problem you want to solve, right? Think of a hypothesis. And then you want to think of a data source. So I'll go through, again, coming up next is a few ideas. So think of something you want to solve. Think of something you want to assert about that problem. Think of what data will help you in proving your hypothesis or disproving it. And then prove or disprove your hypothesis. So, if you're familiar with Reddit, there's a subreddit called Data is Beautiful. And this is an example for you to, so if I can, so what I'm going to do is I'm going to go through a few posts on Reddit, and just to give you a sense of what kind of data is out there and what you can do with it, okay? And this is more on the visualization side of things. This is less about the machine learning side of things and more about how do you visualize really cool data. So let's go through a few tabs. Okay, so what somebody did here is that they found the average temperature. So I don't know how they estimated it, but they found the average temperature trend from 0 BC to 2019 BC. Now, let's watch this video again. So what they're doing is they're measuring the deviation in global temperature from the average between 1961 and 1990. So they're looking at the deviation from, say, I don't know, whatever that average was. So let's say the average was 25 Celsius, okay? So they're looking at the deviation from 25 Celsius. So for most of history, you can see that it was less than the average. So minus 0.1, minus 0.2, minus 0.3 is where it kind of averaged, right? From 25 Celsius. And then it really went down in about 1580. And then in the past, so I wish I could stop this GIF, but I can't. But if you look at just the past, say 10 years or so, the average temperature shoots up, right? It's going to happen now. It's going to happen soon. It's going to happen, right? So in the past 10 years or so, the average temperature shoots up. Now, how did somebody build this visualization? This is a very effective visualization, right? It's better than telling somebody, oh, you know what? We've had the hottest 9 out of 10 years in history in the past 10 years. If you can build a graph that effectively visualizes it, it really adds a punch to your assertion, right? So this is one example. And every post on Data is Beautiful, it has a post called Author Citations. So if you click on View Author Citations, you can see where did they get the data from, and they explain exactly what they do. So I made this visual using R with ggplot and screen to GIF using data from this paper. So this is a paper from the journal Nature, and they publish data. And so he says exactly how he does it. So he used the programming language R, he used a package called ggplot, and he says the raw data is available over here. And he says, and so it basically, they tell you exactly what they did to build that visualization and what the data source is, okay? So let's look at something else. Here's a post on what's the most popular web browser between 95 and 2019, okay? So if you're old, like me, you'll remember the time before 2000 when Netscape Navigator was one of the most popular browsers, right? So let's see if we can run this. So this is a graph again. So it's 96 now. Netscape is losing browser share to Internet Explorer. 98. IE is growing very fast in 99. 2000. IE is eating up Netscape. Netscape ceases to exist almost in 2002. And then Firefox starts growing in early 2000s. The market share of Firefox is slowly growing. IE is shrinking. And then I think Chrome comes onto the market pretty soon now. So Safari, I believe that's the iPhone browser. Okay, so Chrome comes onto the market now. IE is shrinking. Firefox is growing. Chrome is growing, and then it goes on. So okay, so 2014, Chrome is about half the market now, and then Microsoft Edge comes onto the market in the middle of the last decade, and starts growing a little bit. Anyway, okay, so this is not that important, but the visualization is very cool, and somebody made it, and they have their data sources, and they tell you how they made it, and it's pretty cool. Okay, somebody else gathered a whole bunch of data, and they made a map of the United States with elevation tiles. So what is the elevation of each sort of location in the US? And so you'll see that the western half of the US is largely mountains, right? Using this data. You can go down and you can see the citations, you can see where they got the data from, how they built this visualization. It's pretty cool. Somebody else built a map of India just using its road information. So there's actually a government website where you can get all the road information of the US, of India with lat-long coordinates. And somebody built a map with it. And they just built a map of India. So they didn't use like a geographical map. They just used the road information to figure out, where are the roads in India? What does the density look like? And, you can get a pretty good map of India as a whole just using the roads, right? You can see where the mountain ranges are. So, you can see here that this is the Western Ghats mountain range. It's pretty clear, right? Bombay is right around here. And so Pune is just across the mountains. So again, pretty cool, right? And you go down and you can see author citations, see where they got the data from. And when you see this data, I want you to ask yourself, what other questions can I answer? Okay. Somebody else graphed monthly tourism numbers to India again. So this was right when COVID hit. So you can see there's some seasonality, right? In every year there's a peak of tourist arrivals, and then there's a trough of tourist arrivals. And generally speaking, since 2000, the number of tourist arrivals has been increasing until COVID hit, right? So again, you can see where they got this data from, and what they did with it. And then you can ask yourself, what else can I answer? Somebody else built this visualization of COVID transmission in India, and so they looked at again, government reported numbers, and they looked at the total new cases per 100,000 persons. So I don't want to go through the whole thing, but if we watch, for example, say from early this year, and if we look at the transmission per 100,000 people, they visualized the transmission rates per day. And so, the redder something is, the higher the transmission rate. So you can see things kind of heating up in March. And then as April goes on, this is when things start to really take off. And now, almost the whole country is experiencing very high transmission levels in May. Okay, so it stops on 9 May. So this is something, somebody found COVID data and somebody made a visualization of that COVID data. This is called a Sankey graph. So somebody made a graph. Again, this is something, it's just for fun, right? So somebody made a graph of how much it cost that person to pursue their bachelor's at a top-tier university in India. So I don't know why, but they use dollars to represent their expenses. And so they spent a total of about $20,000 And then they broke that $20,000 into fixed cost and variable cost. And then they broke up the fixed cost into tuition fees, other fees, and mess fees, and then variable costs into food, clothing, healthcare, and so forth. And then they broke each of them further down, right? So this is called a Sankey graph. And so this is a way of visualizing a thing. So maybe you can visualize how you spend your time, how you spend your money, you know? So this is a very effective way of visualizing how something breaks down. Somebody else made sort of kind of funny Sankey graph of the experience of trying to find a job as a pilot in the last 4 months. So they sent in 156 applications, and they didn't get replies to 152 of them. And then they got 3 email replies saying that they didn't get the position, and they got 1 phone call from chief pilot laughing that they even applied to the job. So again, this is somebody having a bit of fun, right? But it very effectively visualizes the experience that, you know, the vast majority of the time you send an application and you don't get a response. Okay, so those are some examples of, so the reason that I want to go through this subreddit is that it gives you an idea of the kind of data that's out there, and it gives you an idea of what you can do with it. So the ideas on subreddit were just visualization. If you go through the subreddit, you'll find more analysis. So somebody went through, for example, religious texts, and they figured out, you know, these are the concepts that are most common in this text. And you know, they did some sort of natural language analysis and so forth. So there's a lot of data out there. Pick something you're interested in, do something cool with it, learn some skills, and build something you're proud of, build something that that is useful to people. You know, I've had friends, for example, build a visualization tool for COVID when COVID first came out to understand whether, so, you know, in the US, there's a lot of skepticism about masking. Does masking help? Does social distancing help? Right? And, you know, you guys are lucky in India that, you know, you don't have that skepticism, and people just understand that, you know, masking is common sense and distancing is common sense. But over here, unfortunately, we don't have that. And so one of my friends, they built a tool that tracked the COVID transmission rate and overlaid it with state rules about masking and distancing. And then they used a little bit of statistical analysis to say that, well, you know, masking does really help in reducing transmission, and distancing does really help in reducing transmission. So that's just something that they wanted to do, right? Nobody gave them this idea. Nobody gave them a task. Nobody gave them a question to answer. You know, they just sat at home and said, well, there's data available, and I'm interested in proving that masking is useful. So here's what I'm going to do. So, you know, come up with the project ideas, think of something that's close to your heart, think of something you want to prove, find the data for it, and prove your hypothesis. And I'll end with general advice, but maybe we should take questions before we go further. Oh, Wes, are you still there?
Yes, I'm still
Oh,
here.
fantastic.
I'll just relay the questions.
Okay, thank you.
Picking up from where we left previously. So, one question from a student, Barira, is, do I need to be good at programming to succeed as a data scientist? Maybe you could briefly elaborate on programming in particular, what students would have to do if they are looking to become a data scientist.
Okay, I think so. I think that you have to be at least a competent software engineer to be a good data scientist. Otherwise, you're just leaving the door open to making a lot of mistakes as a data scientist. And you really don't want to make mistakes as a data scientist because, you know, a lot of decisions depend on your analysis. So definitely, I mean, you know, I'm not going to say that you shouldn't do data science because you don't have those skills, but as much as you can, focus on picking up good, solid logic and programming skills in order to improve your efficacy and efficiency as a data scientist.
Great. Another question from a student, Danish Raza, is that, is basic statistics and basic math sufficient for data science, or should they be working on more depth in both statistics and math?
So a basic graph of statistics will get you far. And if you want to focus more, again, on the kind of data science role where you want to do more statistical analysis, then, you'll need more depth. But, a basic understanding is good enough for maybe a machine learning engineer or a generic data scientist or data analyst kind of position. Like I said, there's no good definition of what a data scientist does, right? Every role, every job has a different definition. Every company has a different set of requirements for what they want the data scientist to do. I've seen requirements from companies who think that data scientists should just do everything, right? All the way from understanding business requirements to doing groundbreaking machine learning research. And that's just, it's unworkable, right? And other companies that have more experience, they understand that, you have to have different kinds of roles, but again, they call it data science. So it's difficult to say. It depends on what kind of role you're interested in landing, what kind of skill set you want to build up, what your brand is, what your aptitude is. But again, at a basic level, you should have basic competence in all of the fields that we talked about: statistics, software engineering, basic machine learning, basic data management, basic math, basic programming. You should have at least a basic competency in all of these. And then just depending on where you want to specialize, you keep building your skill set in those fields.
Perfect. One more question is around like data itself.
Okay.
Like your views on structured versus unstructured data and like how effective they could be for data science in particular.
Okay, great question. So one of the things in machine learning is that typically as a data scientist, you're told, here's this data, here's a problem, solve it, come back to me, okay? And many times in real life, many times, that data is not suitable for solving that problem. Maybe it's badly collected. Maybe it didn't collect one critical piece of information, right? So as a data scientist, you have to be comfortable in pushing back and saying, you know what, we have to throw this data out, we have to collect new data, and here's how I want you to do it. So, and this is where the structured and unstructured thing comes in. So maybe the data that they've already collected is structured, but it's structured in the wrong way, right? Or maybe it's unstructured and you need it to be structured because the kinds of learning algorithms you want to run on it run much better with structured data. So there's a place for both structured and unstructured data. It just depends on what you want to solve, right? The advantage of having unstructured data is that you have tons of it, tons and tons of it. It's very easy to collect unstructured data. So if you have a way of making sense and deriving insight from unstructured data, that's typically the way you want to go in, if you can. Collecting structured data is much more expensive, but it can lead to better performance. So it's just a trade-off. And again, I'm speaking very generically here, right? Without knowing more specifics of exactly what you're referring to.
Perfect.
Does that answer your question?
Yes, I think that should be sufficient.
Okay.
Yeah, Danish Raza asked the question if you would like to unmute yourself and maybe respond to say if that was sufficient for you as well.
Yes, sir, I think my question was answered.
Awesome.
Perfect. In terms of other questions, some of them are fairly subjective, like in terms of implementation of data science.
Okay, that's fine.
Agriculture to optimize
Sure.
produce. Like, do you have any thoughts around that? And the other one is around prediction of COVID-19 waves and how could that be used to minimize their casualties. So I guess what you could do is think about how you would, if you had those two data sets, implement this and maybe help Shafiq and Ramesh understand. Thank you.
So these are great questions, and I don't want to, just give you ideas off the bat, because each of these questions, requires a good amount of thinking and understanding. And I don't want to just off the cuff say, here's what you should go do, okay? Because, so as far as agriculture goes, again, think of what problem you want to solve. Think of what problem you want to solve, think of what data you have available, and think of how you can use that data to solve that problem. So can you use, drone images to estimate the yield of a particular crop of land? So that's a hypothesis. My hypothesis is that images are useful in quantifying the yield of land. Okay, so collect the data and prove your hypothesis or disprove it. Okay, and once you do that, you can move on to a more complicated problem. How do I exactly measure the yield? What's the best way of doing it, right? Are there any complications? Is there anything that I'm missing? So you sort of craft your solution around the problem you want to solve. Now with COVID data to estimate, so again, COVID is actually something that yields a large amount of data, right? So you have this institute in the US called IHME. It's actually based very close to where I live, the Institute for Health and Metrics, something like that. And so they have these models, and they said that with distancing, we predict that COVID cases will continue to rise at this rate for the next 2 months. So there's modeling algorithms, there's predictive algorithms, there's statistics. There's a lot you can do with COVID data. If you have good data to start with, you can look at forecasting algorithms. You can look at predictions, modeling. These are all different things, by the way. Forecasting is different from modeling, is different from predictions. And so you can do all of these things if you have that data set. As to how we can minimize transmission, again, so this is the intersection of data science with public policy, right? And this is something that's, again, a very new field. How do public policymakers use insights from data science to inform public health policy? This is a very new area, right? We don't know the best way to do it. And so if you actually do any work in this area, it'll be fairly groundbreaking. I don't have a clean answer for you how to do it, but problems you can ask yourself are, for example, can I find data from a state where they had public health interventions? And can I find data from a state where they didn't have public health interventions? And then can I make sure that this data is comparable to this data? So that if I infer an estimate from this population, is it comparable to an estimate from that population, right? So these are the questions you can begin to ask in service of answering the larger question of how can I prevent transmission? Does that answer your question? Feel free to unmute yourself. Feel free to unmute yourself and ask any follow-ups if you have any.
Otherwise, and Ramesh, if that answered your question, you could go ahead and respond to it that way.
Let's move on, always. They can speak up if they have any follow-ups.
Another question is, do you have any references for publications, websites, or books that you read or attend, that are helpful for your work?
Right. So I did go over the list of books and conferences as well. So I mean, I'm not saying that you have to, as a BTech student, you have to go through all the conferences and go through all the papers. Even I don't do that. But what I'm saying is that at least go through the best papers, understand why they were best papers, what problems are they solving, where is the field at, right? So at least you can do that for the top conferences in machine learning and statistics and data management. KDD is very good. I forget what KDD stands for, knowledge and data discovery, I think. So KDD is a very good, a very practical, application-oriented conference. So you can look at the best papers from KDD. You can look at the best papers from ICML, the International Conference on Machine Learning. So if you're interested more in the academic side of things, more in the researchy side of things, definitely go through those conferences and figure out, the papers that stood the test of time and best papers from recent conferences.
Perfect. I'm not sure how much time we have remaining, but there's an additional question I could ask that way.
Yeah.
So one student is asking that they've participated in ML competitions. I think what they're trying to understand is how representative are these sort of participating in a competition at a university and working on a machine learning model there versus working as a data scientist in real life.
So you may not like my answer. I think that Kaggle competitions and university competitions they're fine. They're fine for building up your skills, but they're not a substitute for real world experience. Especially with Kaggle, with university competition, you have a very well curated data set. It's generally fairly clean, generally speaking. There still might be some cleaning that needs to be done, but somebody's already made a first pass through it. And usually they're not super large, usually speaking. I could be wrong. And if I am wrong, somebody please correct me. And so they're good in the sense that you're playing in a sandbox. It's good to develop your skills. It's good to develop your own models. It's good to understand programming languages. It's good to understand data science paradigms. It's good to sharpen your teeth, but they're not representative of actual problems you'll be solving as a data scientist like a large corporation, for example.
Hello.
Yeah.
Now, may I ask a question that to be a good ML engineer, in which areas we should have to be a perfect, and which softwares you used in your daily routine? Thank you.
Okay. So a machine learning engineer, generally speaking, is somebody that has a basic understanding of machine learning algorithms. So typically, a machine learning engineer will not be building the models, but they'll be building the infrastructure around those models. So they'll be building infrastructure to retrain the model. So you have to understand what the model is, what the features are that go into that model, and build data pipelines to gather data and to periodically retrain that model. Okay, and then as a machine learning engineer, you'll be building the infrastructure around exposing that model to service calls from outside. So you want to know how that model works. You want to know whether it's slow or fast. You want to know what will make it fall apart. So you have to understand machine learning. Maybe not to the research level where you're doing groundbreaking research, but you want to understand the basics of the machine learning model, and then you want to understand a lot about the software around it. So how do I build data pipelines that collect data, that store data, that call the training method to train that model? How do I gather the features in real time? How do I call that model in real time? How do I build monitoring software around that? What are the metrics that I want to keep track of? So that's what you want to do as a machine learning engineer. So you want to have basic machine learning knowledge, and you want to have really good software skills.
Could you please share which softwares you are working on now?
Okay, so again, this is an unpopular take. It doesn't matter what software I'm working on. Okay, programming is programming. I will tell you, I've done a bachelor's, master's, and PhD. I've never taken a course on learning a specific programming language. Never, ever. I've never taken a course where I learned Java or Python or C++. Okay, if you know programming, you can pick up any language in a day or two. Okay, right now I work mostly on Python, and even in the way that we productionalize our solutions, we mostly use Java and Python. But we build our own sort of infrastructure around everything, right? So, but again, so if you're not working exactly where I work, you would generally use Python, even for the service side of things. So you build a Flask application, you use GUnicorn to serve a machine learning model, and then you place it behind a web server, like a WSGI web server or something. So if you know Python very well, it will serve you very well. Okay. I would recommend you also know Java and C++. And as far as tools go, in Python, I would recommend that you know pandas. I would recommend that you know NumPy, SciPy, scikit-learn. I would recommend that you know how to use Spark. And especially now in 2021, I would recommend that you know how to use cloud technologies. So how do you use Spark, for example? So, at home, you don't have access to 100 machines, right? At your average company, you don't have access to 1,000 machines to run computation on. But what you do have access to are cloud services, Amazon, Google, Microsoft, right? And whatever other cloud services there are. So I would recommend that you understand how to use cloud services. How do you distribute your data across cloud services? How do you call, for example, and again, I'm very biased because I've only ever used Amazon cloud services. So how do you use AWS Lambda? How do you use AWS EMR, for example? How do you use Spark on AWS machines? How do you spin up 100 machines, and how do you distribute computation and data across those 100 machines? So that's, again, something you really want to know as a machine learning engineer. And that's more important, actually, than well, I won't say more important, but it's very critical to know how to use those services and how to stitch different services together. How do you stitch Lambda and AWS Batch and Amazon Elastic Container Service? How do you stitch all these together to make a pipeline that works for your application? And if you know Python, you should be good to work with most of these cloud services and to work with most data analysis applications.
Thank you so much, sir.
You're welcome. Let's move on, Uwais. Also, Uwais, please feel free to chime in if you think that something's incomplete or I'm going off in the wrong direction. Your experience is valuable as well. I know that you're a senior data scientist now, and you should definitely not hold back from sharing your insights as well.
No, thank you so much. All the answers were great. So if I feel like there's anything that I need to add, I'll definitely add. So thank you.
Always, if you are done, I think Najib, if he's there, I would request him to.
Sure. What I can do is I'll just take a screenshot of the questions and I'll forward it to Hidayat Bhai so that he can answer them later. And Mu'tasim Najib Saab can pick it up from here and conclude the session. Thanks for
awesome.
Yeah, thanks, Uwais. And Hidayat, it's an excellent session. Congratulations. I think you anticipated the needs of the audience, you connected the dots, and you explained with a lot of storytelling and anecdotes. So great job. Thank you very much for the presentation.
Thank you. It's my pleasure.
Yeah, so I just want to take I know it's getting late, just wanted to take a few minutes and talk about the upcoming Ask Anything session that we've been communicating with you. So just to give you some context, this program has employed two types of forums. One is the group sessions, example of which is the session that you just had. And we have predetermined a set of topics, soft skills, technical skills, and we have experts like Hidayat who give an in-depth talk and make the session very interactive. So that's one forum. The second forum is your personalized session. So this is where mentees are assigned to mentors, and you develop a trusting relationship, and they will help you guide both in terms of working on your deliverables for this program, as well as helping you with deciding your career choices and what are the next steps in your journey. Now, the Ask Anything session is a third type of forum that we are introducing in this program, and here we have mentors with different backgrounds, very successful journeys, life experiences, who are available to you all for hour and a half, where you can ask questions that are impromptu, or you can send them in advance. And the idea here is, we have a very diverse set of mentors. Some are technical, some are leaders, and they may not be able to answer every question pertaining to your career or your choices. So this is where you have people with different backgrounds coming together and answering your questions. Now, Ask Us Anything should not be taken literally. I mean, there's still some context around here. What we'll do is we will publish the bios and experience levels of the mentors who will be in these sessions. And you're going to get the biggest bang for the buck by asking questions pertaining to the experience that these mentors are going to bring in the session. So don't ask us the meaning of life type of questions, for example. You may get an answer, but that may not be accurate. So Ask Us Anything really means within the context and the direction of what this program is helping you with. So I encourage all of you to join these sessions. These are going to be very valuable. And you will also hear what is on the mind of your peers, of your other students. And so this is a very effective way of communicating what may be common questions on people's mind, as well as interacting with each other. So that's just a sort of lead in to the session that we'll be having called Ask Anything session. Basharat, back to you.
Yeah, I think that's good enough, Ajib. And then the mentees should make note and attend this. And it's a wonderful opportunity for you to get your doubts clarified. And if you have any pertinent questions, queries where you are stuck, you can discuss them with the mentors. I think that's all. Is anything else?
That should be it, Basharat.
Yeah.
I think that should be sufficient.
Thanks, everybody. Thanks, Hidayat. Thanks a lot. Very shukriya aapka. And I'm sure the students were looking forward to this session.